6.4, we really dig into the properties of the definite integrals. Okay, basically what you can and can't do. Let's see, is there anything up there I need to? Yeah, we're going to, as I said, we're going to be looking at applying some of the properties, how we can add, whether we can add, subtract, those type of things, whether they can break up, whether we can multiply, all of that. Now, we've already talked about the area that goes below the x-axis is negative, right? So we've already talked about that. You have to keep that in mind, and that will still come into play. Area below the x-axis counts as negative area. The total area A and B for some curve is really a net area, where the total area below the x-axis and above the curve is subtracted from the total area above the x-axis. And again, it just has to do it. Whatever's below the x-axis, it's negative or you're subtracting it, 1 to 2, depending on your situation. Now, some notation. I went ahead and wrote in a couple of definitions. You've heard me read this integral notation lots of times so far, yes? And this is just kind of an official, so you can put it in writing. This notation is read as, now, I don't usually say the definite integral, but you'll hear me say the integral from a to b of f of x, and then the part I usually just say dx, but that dx is saying with respect to x. It's telling us with respect to what variable are we going to be integrating and working. So, now, some component parts. A and B. What have I referred to A and B as? Referred to A and B as my lower and upper, I think I've used the word limits maybe. I'm trying to think what other, I think that's probably what I have here. Yeah, here I have written in as the upper limit of integration and the lower limit of integration. I know I have definitely, and honestly, don't really have room to write the other part, so B is your upper limit of integration. A is your lower limit of integration. The little curly thing is our integral sign. Okay. Down below, this whole expression is the definite integral. And I will say it's a definite integral because it has the boundaries or the limits of A and B. You might hear me say boundaries instead of limits, I guess. But it's a definite integral. We'll talk about indefinite integrals eventually too. F of x, part of me wants to say it's the function we're integrating, but official vocabulary is it's the integrand. Now, do we know how to spell that? Okay, so that f of x is the integrand. And then dx is stating the variable with which we are integrating, so it's just saying the variable of integration is x. Okay. I've been teaching you from day one, integrals can be used to find area, right? Derivatives, we talk about slope of the tangent line. Integrals, we talk about area. So the net area or displacement, and when we talk about area, it's used to find area. It's the area under the curve. And so when we talk about area under the curve, it's area under the curve, or between the curve and the x-axis. And then from A to B means it's from a vertical line x equals A to another vertical line x equals B. Okay, so the net area or displacement is bounded by the x-axis, the function f of x, so whatever that curve is, and then A and B. Okay, so you've got everything has a border, so to speak. Now, some of this I feel like will seem familiar. Because I look at the next page. I feel like you know what to do on A. So when you're ready, you can flip to the next page. We have a big old fun graph here. Use the graph below to evaluate each of the following. Note that the graph of f of x consists entirely of line segments and a semicircle on the interval from -8 to 13. Semicircles, quarter circles, they use those a lot in Lesson 6-4. Okay, so we'll definitely talk about how we can do that. And I think we even talk, in Lesson 6-4, we even talk about the equation somewhere. Yes, we will. So, okay, I think you guys are all caught up, right? Use the graph below to do this. So A, the integral, sorry if I want to be official, the definite integral from 0 to 7 of f of x with respect to x. What is this asking me to do? Find the area from 0 to 7, right? The area under the curve or between the curve and the x-axis. So, what do we have here from 0 to 7? Trapezoid. How do we do that trapezoid? Guess I could put it right here, couldn't I? 1/2 times. Okay, height times base plus base. The height is 4, and my bases are 3 and 7. So half of 4 is 2, times 10 is 20. I'm trying to think, do I have to break that up later? No, I do kind of have to break that up later, but that's all right. 20 is that whole trapezoid. We'll have to find parts of that, a different part of that later. Okay, B, now what? Area from 0 to 13. So we already know 0 to 7, yes? 0 to 7 is already that 20. Plus, what are we going to have to do now? Trapezoid down below. What about this trapezoid down below? It's going to be negative, right? So I said plus out of habit, but really it's going to be plus a negative. And in order to do this, it's what? 1/2 times height of 3 times bases of 6 plus 3. Tell me if my math is off. 6 plus 3 is 9. Times 3 is 27. Half of 27. 27 halves. Let's say, do we want to go fractions or decimals here? I guess 27 halves is 13.5 if you want to go that way. So then you're doing 20 minus 13.5, which is 6.5. Now I am going to go ahead and put up here that that piece was 13.5. Okay, what about from -6 to 0? We have a half circle, excuse me, semicircle. That's what the directions called it, right? Half circle. What's the area of a circle? Right. It's not 2 pi r, that's circumference. Nope, now you're talking volume.
Pi r squared.
Plain old pi r squared. Is this a formula we need to know? Yeah, just saying. Now, so circle is pi r squared. So this is a semicircle. We're officially going to do 1/2 pi r squared, yes? What is my radius here? Disagree? Disagree?
3.
3? Because for a radius, I need to go, where would my center be? My center would end up being here, right? And any direction I go out to the circle has a distance of 3. So since my circle is 6 across, it has a radius of 3. Oh, lovely. I have been expressing this as 9 pi over 2. What am I forgetting, though? It's negative. Okay. D.
0.
Integral from 3 to 3 is 0. That's officially kind of one of our properties. You just, when your upper bound and lower bound are the same, you're going from one thing to itself. There's nothing in between. It's 0. What about 7 to 0? Have we talked about this yet? I'm trying to remember.
Is this when you flip or make it negative?
Yeah. So we want our bounds to go from smaller number to larger number. If for whatever reason they give you something that doesn't go from smaller number to lower number, we are going to flip it. And when we flip it, it is multiplied by a negative. So this is going to be negative integral from 0 to 7 of f of x dx. So thus, my answer here is negative 20. Because back on part A, we already found the area from 0 to 7 was 20. So from 7 to 0, we're talking negative. Basically, you're moving left now is what you're doing. Okay, what about F? That way I don't want to use any different color there. First of all, should we talk 10 to 4? No, we should probably talk from 4 to 10. So I'm going to rewrite this as the negative integral from 4 to 10 of f of x dx. So that means I'm doing the negative of whatever I find here. Okay, what are we doing? 4 to 10. So we got 2 new trapezoids here to talk about. I don't know that I really have room to put my trapezoids down here, so I'm going to put them up here. The 4 to 7 is going to be 1/2 times the height of 4 times bases of 3 plus 1. So this piece is going to have 8, if you will. Ignore the 20. Remember, the 20 was the whole thing. And then down below, it's 1/2 times a height of 3, and then bases of 3 plus 2. (15 halves), 7.5. So I have my negative out front already. Then I'm going to put this in parentheses. From 4 to 7, it is 8. And then we're adding on what? Negative 7.5. Or in other words, we are subtracting 7.5. So this is the negative of 8 minus 7.5. So we end up with negative 0.5. Are you okay with my math? Okay. Oh, gee. Negative 8 to 13. one thing we don't know, isn't there? What do we know about that little end piece? It's a triangle. Triangle is 1/2 base height, so 1/2 times 2 times 4. So that triangle has an area of 4. Oh, this is the one that I wrote multiple different ways. So if I look at the pieces, I know there's a 4 minus 9 pi over 2, plus 20. I was going to say minus 13.5. I think I'm going to go to 27 halves here. In the effort of, I see other fractions. Although I guess my notes I had 13.5. You want to clean this up. So we clean this up. We've got 4 and 20 is 24. And then if you take off that 13.5, that puts us at what, 10.5? 10 and a half? So different ways to write this. I mean, the not very good way is 10.5 minus 9 pi over 2. That's kind of, I've got a decimal and a fraction there. If we look at 10.5, that's 10 and a half. 2 times 20 plus 1. And so that is 21 halves minus 9 pi over 2. Beware, I don't think you'd see this answer on AP Calc because you can put them together. And so I feel like what you'd see after all of this is 21 minus 9 pi all over 2. Okay. Are we good with that one? Okay, H. F prime of negative 6. I feel like this is a shot in the dark, but that's all right. What are they asking us for here? The derivative at negative 6. Derivative is slope at negative 6. Now, let me double check. What was this graph? This is the graph of f of x, yes? Okay. So the derivative is the slope. What is the slope at negative 6?
DNE.
What?
Is it DNE?
Because what do we have right here? Okay, cusp, a hard point. Okay, not a nice, smooth, flowing, continuous curve there. It's continuous, but so we do have a cusp there, or a hard point. And so this is you could say DNE, or you could say undefined. The slope is not defined, so the derivative is not defined at this point. Now, keep in mind, this was the slope at negative 6 is what we just did. Okay. Second derivative at 6. F double prime of 6. A little bit different situation here. My recommendation would be to ask you to think about the first derivative here. Okay, and I guess I could even go as far back as if I said f of 6, what am I asking for there?
Your y value.
My y value, right? At x equals 6, my y value is 2. Okay? If I say the first derivative at 6, what am I asking for? The slope. What is my slope there? Yeah, rise -2, run 1. So my slope of that line is -2. What about the second derivative then? What?
Isn't the derivative of the derivative?
Okay, so we can talk about being the derivative of -2. And what is the derivative of -2?
0.
0. Derivative of a constant is 0. So this is just 0. Officially, we could also talk about, derivative talks about concavity, but we don't have concavity with straight lines either. Okay, so that second derivative is 0 there when you're talking about a linear function. Okay, dig deep, dig deep. Average rate of change. You don't get to forget calculus, that's the problem. Yep. Average rate of change, f of 5 minus f of 0 over 5 minus 0. F of 5 is 4. F of 0 is 0 over 5 minus 0. So we get 4/5. We've slept a lot since then, haven't we?
Couple of times.
Just a couple? Hope you've slept more than just a couple. Okay, K. True or false?
True.
Man, he just says true, just like that. Did you think about it? No. Dang it. Okay. Thought maybe you thought about it and you'd already reasoned it out and had your answer of true or false, but
Am I right?
Is he right though?
I don't know. I mean, how can we figure this out?
That's true. 2 to 2 and 2 to 4, so again you go with 0.
Okay. So if we're just trying to think logical, this is going to be the area from 0 to 2 plus the area from 2 to 4. And we want to know, does it equal the area from 0 to 4?
Yep.
Logically, it makes sense, yes? And it does. If you plug the numbers in there, I think you end up with 4 plus 8 equals 12. Okay. So you could say 4 plus 8, I think it's equals 12. Now, that is one of our, I think when we turn the page, yes, this is one of our properties of integrals that you need to be comfortable with. And the idea is, you see the 0 and the 4, right? They share a limit. Nope, I can't get in there, can I? Okay, just do it like that. They share a limit. If you have two integrals and you're adding them, and an upper limit on one is the same as the lower limit on the other, you can add those two integrals, and they'll have the lower and the upper limit of the others, if that makes sense. Yes?
So this is going to be like helpful if it's like 0 to 13, but then you can like, because you can split them, you split it down and then you do subtraction on that one?
Mm-hmm.
Okay.
Well, wait, what were you saying?
Well, like you said, you can split it and add it up if it has the same, so like you do 0 to 7 and then 7 to 13. But like if they had written it as 0 to 13,
Yeah.
you could split it.
Like if you know some of those pieces, yeah.
Oh.
Okay. And then, over which values of x is f of x not differentiable?
True. Sorry.
False.
Thoughts?
Let's start with things.
Okay, so it says which values of x. So x equals which values? Not a true, not a false, not a yes, not a no. We've already talked about one of them, if that gives you a hint. -6, because it was a corner, right? It was a cusp, so we can't differentiate there.
Can we say -8?
We won't say -8 because,
It's just PN now.
yeah. Okay, what'd you say after -6? 0, I could go there. Dos, got it.
No, Cinco.
Cinco?
Why are we talking in Spanish?
I don't know. I'm just going with the flow here. Okay, we got cinco, we got 5.
Ocho.
Okay.
Once.
You just wanted to say that. I know you did. 7.
Siete.
This
What?
is
No, this is just not right. We didn't go in order.
13.
I know, I debated. I don't know if anyone was watching me and saw my pause, like,
I did.
do I leave a gap? Do I not leave a gap? Do I let him go with it? I should have left a gap, but you can rewrite yours if you want. If it's not worth that much hassle, then. Okay, all of these points, including 7, and it's hard to tell because I've drawn on mine, but here's the deal. Those 2 lines that connect at 7 do not have the same slope. So they are not just a smooth curve. It's not much of a corner, but there is a corner because they don't have the same slope. Does that make sense? That is what your connection needs to be there. Okay. Moving on, moving on. We are learning some of these properties of integrals. Some of them you already know, honestly. I don't know, she kind of hinted at, gosh, most of these. We just haven't officially had them, so now we officially have them. So the definition of the definite integral of f on the interval a to b specifies that a is less than b. So that's why it's always weird when you have the bigger one down below, and that's why we talk about flipping it. Now, however, it's convenient to extend the definition to cover cases in which a equals b or a is greater than b. So you've got this one, right? If f is defined at x of a, then the integral from a to a equals 0. When your lower and upper bounds are the same, it's 0. Been there, done that. Number 2, if f is integrable, whatever word I'm trying to say there. The integral from b to a, okay, that's that awkward thing of the bigger ones on bottom, is equivalent to the negative of the integral from a to b. So anytime you need to flip the integral for some reason, it's multiplied by a negative. Okay? Additive property. This is what we just did. The integral from a to b is equivalent from the integral from a to c plus c to b. So notice, what do you see here? No pun intended there. The c's are overlapping, right? So if you're going from a to c and c to b, c is some value in between a and b, then this is the same as the integral from a to b. That's a very handy one to have. This one here says if k is a constant, then you have the option of taking that k out front of the integral. So if it's the integral and it's k times some function, you can pull out that factor. It's kind of like factoring the k out front. Yes?
Is it like I think it was 6-2 when it was delta x, she would put it out front on her notes?
Yeah, I think
Because that confused me for a while because I couldn't find
we were
delta
dealing more
x.
with limits there. That was more because that was the limit of the sum, but yeah, similar. Okay. 5. This is one, I'll be honest. I have never seen this property written this way, and I guess it's because I've never introduced the properties before I've always introduced, okay, how do we find these integrals? Like, how do we find an antiderivative? And then I've introduced properties. So, but this is saying if your integral is just a constant, aka there are no variables, then it is equivalent to the constant value times upper limit minus lower limit, so times b minus a. We'll see that one come up several times. Once we learn how to integrate this, you don't really have to use this property once we learn antiderivatives, but we're not quite there yet. And then the bottom one, if you have two terms or more than two terms being added or subtracted within an integral, they can be broken into separate integrals. Okay, so when you have pieces being added or subtracted. Okay, let's try these. We're going to use these properties down at the bottom of this page. Okay, notice we have up top, the integral from a to b of f is equal to 8. The integral from a to b of g is equal to -3. And the integral from a to b of h is 5/2. Okay, a is asking us, what is the integral from b to a of g? Agree? Because if I officially write this, this is the negative integral from a to b of g of x dx, right? So thus it is the negative of -3, which is +3. B, the integral from a to b of 2 times f of x dx. Is equal to 16. What's the property I'm using? Okay, which the one that says you can pull the constant out front. Is it number 4? Yeah. So officially the rule is I can pull this 2 out front, and that's 2 times the integral from a to b of f of x dx. So then you have 2 times the integral of from a to b of f, which is 8, and that is 16. Okay, C. Integral from a to b of 5 dx. This is property number 5. Property number 5. And notice, what do we have in the integral? A 5. Is there any x? There's a dx, and that's just saying with respect to x. But there's no variable. So this is just saying that you can take that constant and multiply by upper limit minus lower limit. So 5 times b minus a. That one came up a lot in homework. D. Integral from a to b of 5 plus g of x dx. Okay, so officially the plus sign says I can split this into 2 integrals. The integral from a to b of 5. Now I put a dx with that because I want to always have that dx telling me it's with respect to x, plus the integral from a to b of g of x dx. So it's almost like you are distributing that dx and it has to go in each part. So now the integral from a to b of 5 dx is going to be 5 times b minus a for the first one, plus -3, so -3. Clean up? I mean, you could distribute the 5, but we're still not going to have like terms. So I think the answer key is usually leaving things like this. E. E is a situation where I'm almost tempted not to rewrite the property. So I totally get it if you guys don't rewrite the property. I'm going to be official, but two functions being subtracted can be rewritten as 2 integrals, right? The integral from a to b of f of x dx minus the integral from a to b of h of x dx. And what do we have here? Oh, fun. 8 minus 5/2. Okay. And my brain would say 8 is 16 halves, and 16 halves minus 5 halves is indeed 11 halves. F. What is this saying? Sound effects and everything, huh?
Yeah.
Okay. Jacob's showing them, I don't know, colliding into each other, mashing together. What is this going to be equivalent to in terms of integrals? This is the integral from A to B, and it's because the 4's overlap, right? The upper of one is equivalent to the lower of the other, so we can put them together. This is the integral from A to B of h of x dx, which is equal to 5 halves. I like that page. Maybe I'm the only one, but I like that page. Okay. Example 3. Find the following. If the integral from 1 to 5 of 3 times f of x plus 4 dx equals 34, find the integral from 1 to 5 of f of x dx. It's a big old fancy equation in my brain. And that's what I'm going to treat it as. Where the variable I'm trying to find is this right here. This is my variable. Like this is a big old x that I'm trying to find. Take what we have and break it up. This can be broken into 2 integrals, yes. And the 3 on this one integral can be pulled out front. So that's what I'm going to do first. I'm going to say 3 times the integral from 1 to 5 of f of x dx plus the integral from 1 to 5 of 4 dx, and it all equals 34 still. It's a big old equation, guys, because I am trying to solve for the integral from 1 to 5 of f of x dx. I don't care which way we do this, but what do you know about the integral from 1 to 5 of 4? 4 times 5 minus 1. So I'm going to keep this as 3 times the integral from 1 to 5 of f of x dx plus, since this has no variables, I'm going to change it to just constants. It's 4 times upper minus lower. My equation still equals 34, yes? See where we're going with this? I can clean that up. I didn't because I wanted to write it out long way. 4 times 5 minus 1 is going to be 16. So I have 3 times the integral from 1 to 5 of f of x dx plus 16 equals 34. Do you see your final 2 steps? We're going to what? Subtract 16. So then I have 3 times the integral from 1 to 5 of f of x dx is equal to whatever 34 minus 16 is. 18. And then if it's 3 times this integral, we're going to divide. So the integral from 1 to 5 of f of x dx is equal to 6. Intimidating looking, but not bad. Kind of algebra. It's algebra. I mean, you know. Okay, where are we at? My watch says 112. So 112, 113. Okay. This next part talks about even and odd. Do you guys remember your definitions of even and odd?
Could it be divided by 2?
No. Not even in odd numbers, even in odd functions. So the fact that an even function is a function that is symmetric across the y-axis, and the odd function is a function that is symmetric across the origin. You were already right x-axis, weren't you?
No.
Or yeah. Okay. And that just has to do with if something is symmetric across the y-axis, same over here as it is over here. That means if you know the area on one side, you know the area on the other side. Symmetric across the origin means if you know an area like in quadrant 1, same area is over on the other side but also down below. So we will have to talk about example 4, and we have example 5 left. And all of them are basically using our properties, rolling out kind of a picture, and helping us find the area of the interval. So